In this video, I'll provide an overview of promoting and casting variables. In some circumstances, the compiler changes the type of a variable to a type that supports a larger value. This action is referred to as promotion. Some promotions are done automatically by the compiler if data wouldn't be lost by doing so. You can see two examples of these promotions here. If you assign a smaller type, the 6 on the right of the equal sign, to a larger type, the long number on the left of the equal sign, and if you assign an integral type to a floating point type, as seen here, assigning an integer to a double number, because there are no decimal places to lose. Before being assigned a variable, the result of an equation is placed in a temporary location in memory. The location size is always equal to the size of an int type or the size of the largest data type used in the expression or statement. For example, if your equation multiplies two int types, the container size will be an int type in size, or 32 bits. If the two values that you multiply yield a value that's beyond the scope of an int type, such as the example equation here, which is too big to fit in an int type, the int value must be truncated to fit the result into the temporary location in memory. This calculation ultimately yields an incorrect answer because the variable for your answer receives a truncated value, regardless of the type used for your answer. To solve this problem, you can set at least one of the variables in your equation to the long type to ensure the largest possible temporary container size. The same issue occurs with other data types. Before being assigned to a variable, the result of an equation is placed in a temporary location in memory. If the two values that you used yield a value that's beyond the scope of an int type, such as 7 divided by 2 equals 3.5, the value must be truncated to fit the result into the temporary location in memory. This calculation ultimately yields an incorrect answer because the variable for your answer receives a truncated value, regardless of the type used for your answer. So to solve this problem, you can set at least one of the variables in your equation to the double type to ensure the largest possible temporary container size. Typecasting lowers the range of a value, chopping it down to use a smaller amount of memory by changing the type of the value. For example, by converting a long value to an int value. You do this so that you can use methods that accept only certain types as arguments, so that you can assign values to a variable of a smaller data type, or so that you can save memory. The syntax for typecasting value is identifier equals target type in parentheses value, where identifier is the name you assign to the variable, value is the value you want to assign to the identifier, and target type is the type to which you want to typecast the value. Note that the target type must be in parentheses as seen in the two casting examples here. The loss of precision with casting can sometimes lead to situations where numbers are truncated, leading to errors in calculations. In the potential issue here, the code in line 3 causes the number to be chopped off. The bottom example shows a safer example where there's no data loss in line 3 because mylong has been given a long number with only zeros in line 2, so only zeros are lost when truncation occurs. And here's an important caution. If you typecast a float or double value with a fractional part to an integral type such as int, all decimal values are lost. However, this method of typecasting is sometimes useful if you want to truncate the number down to a whole number. For example, 51.9 becomes 51. Assigning a variable or an expression to another variable can lead to a mismatch between the data types of the calculation and the storage location that you're using to save the result. Specifically, the compiler will either recognize that precision will be lost and not allow you to compile the program, or the result will be incorrect. To fix this problem, variable types have to be either promoted to a larger type size. Variable types have to be either promoted to a larger size type or typecast to a smaller size type. In the top example, the compiler assumes that because you're adding int values, the result will overflow to the space allocated for the byte created in line 3, because bytes only have 8 bits of memory. A byte, although smaller than an int, is large enough to store a value of 100. However, the compiler will not make this assignment and instead issues a possible loss of precision error because a byte value is smaller than an int value. To fix this problem, you can either typecast the right side data type down to match the left side data type, or declare the variable on the left side, num3, to be a larger data type, such as an int. The Java Technology Compiler makes certain assumptions when it evaluates expressions. You need to understand these assumptions to make the appropriate typecasts or other accommodations. Assumptions are that most operations result in an int or long, byte, char, and short values are automatically promoted to int prior to an operation. If an expression contains a long, the entire expression is promoted to long. Also, if an expression contains a floating point, the entire expression is promoted to a floating point. Finally, all literal floating point values are assumed to be double. In the following example, an error occurs because two of the three operands, A and B, are automatically promoted from a short type to an int type before they're added. In the last line, the values of A and B are converted to int types, and the converted values are added to give an int result. Then the assignment operator, the equal sign, attempts to assign the int result to the short variable, C. However, this assignment is illegal and causes a compiler error. As you can see by these possible solutions, the code can work if you either declare C as an int in the original declaration, or if you typecast the A plus B result in the assignment line. This code example calculates a person's age in days and seconds. Because the age seconds variable is declared as a long, one of the literal values used as operands in the assigned expression must be initialized as a long value using capital L, so that the compiler will allow the assignment, as you can see in the circled portion of line 7. The potential problem demonstrated here could cause compiler errors because we're declaring int numbers in the two lines of code, but the last number on both lines is a real number, not an int, and we know that because they both end in 0.0. There are two possible solutions here. First, you could declare num1 and num2 as double types, or you could typecast num1 and num2 as int types in the assignment line. Just as integral types default to int under some circumstances, values assigned to floating point types always default to a double type, unless you specifically state that the value is a float type. For example, the potential problem here causes a compiler error. Because 27.9 is assumed to be a double type, a compiler error occurs because a double type value cannot fit into a float variable. Both of the following solutions will work correctly. In the first solution, the F notifies the compiler that 27.9 is a float value. In the second solution, 27.9 is cast to a float type.